Welcome to the final chapter of Further Mechanics 1. Here we're looking at chapter 5, where we're going to look at elastic collisions in 2 dimensions. The first part of this chapter is looking at oblique impacts with a fixed surface, so where a particle moving in 2 dimensions hits a fixed surface. So I guess you can think about a snooker ball, for example, hitting a cushion on a table, something like that. And then later on, we'll be moving on to the final part of this chapter, is where we're looking at 2 particles colliding in 2 dimensions. So again, you can think of it as 2 snooker balls, something like that, colliding. So rather than the way they do it in the book, I'm just going to give a simple example first to show that this, essentially there's nothing new to learn. We're just going to use our knowledge from chapter 4, where we looked at collisions there, and put those together to understand what's happening when we have a particle colliding with a fixed surface. So in this small example I've got here, I've set a particle moving with a speed of 6 meters per second, an angle of 30 degrees to the horizontal, and then leaving with a speed of v. And I've set the coefficient of restitution between the fixed surface and the particle as being 1/2. Now what we're going to do is look at resolving into 2 components. So if you like, after the event, we're going to have the horizontal component of v, which I'll call vx, and we will have a vertical component of v, which I will call vy. And what we've got going into our collision, immediately before the impact, if I use the green pen here, we are going to have a speed of 6 cos 30 degrees, resolving our speed there, so we're parallel to the plane, and into the plane we are going to have a speed of 6 sine 30 degrees before the impact. Now it's important to note, trying to keep this as big as I can, the impulse provided in this collision is going to be at perpendicular at right angles to the surface. So if you like, we've got the impulse is going to be provided in that direction, which changes the direction obviously here from into the plane to in the other direction there. Now it's important to note that that happens at right angles to our surface. So horizontal to the surface, or I should say parallel to the surface, there is no impulse being provided. So therefore the speed directly before the impact is going to equal the speed after the impact. So straight away, if we look at this component here, we can say that the horizontal component of v is simply going to equal 6 cos 30 degrees, which is going to be 3√3. Now, looking perpendicular to the plane, we use our coefficient of restitution formula. So if we just remember from chapter 4, E is the speed of rebound divided by the speed of approach. So in this case, looking in these terms, we've got 1/2 is going to equal the speed of rebound, which is our vertical component of v, divided by the speed of approach, which was 6 sine 30 degrees. Now obviously sine 30 degrees is 1/2, so 1/2 of 6 is 3, so therefore vy is going to be 1/2 of 3, which is 1.5 meters per second. Now, although I've done it in the full work there, just to remind you of the formula we used in chapter 4, I can just look at it here as well. If I know that the speed going into the plane is going to be 3 and the coefficient of restitution is 1/2, then coming back the other way, we can say straight away that the vertical component of v is going to be 1/2 of 3, so 3/2 or 1.5 as we just said. So therefore we have our 2 components. Velocity v of x, the speed, the horizontal component of that in that direction is going to be 3√3, and the vertical component there is going to be 3/2. So to find the speed of v, or the speed after the collision, we simply have the square root of 3√3 squared plus 3/2 squared, and once we work that out, that is going to give us a value of 5.4 meters per second to 2 significant figures. Now, the other thing we're asked to find is the angle of deflection. So I'll just make a note of that at the bottom of the question here. So the angle of deflection. So here, if I call that angle alpha, my angle of deflection is going to be 30 plus alpha. So we add the angles that we go in here. Now, the reason for that, I often get asked this question. If you imagine we were continuing through that point of collision there, so we've got 30 degrees from the horizontal, and it bounces back with our value, which we'll find out in a moment, of alpha, then you can see that the actual angle between our two speeds is going to be the 30 degrees plus alpha. Okay, so it's just really finding the angle between our two speeds or velocities when you add the direction to it. So you've got 30 degrees, obviously because they're vertically opposite, plus the angle alpha there. And to find alpha, we've got the tan of alpha, similarly just using this same components here. So the tan of alpha is going to equal 3/2 divided by 3√3, and that leads to alpha being 16.1 degrees. So finally, the angle of deflection is going to equal 30 plus 16.1, which is 46.1 degrees. So everything they have in the book does make sense as well, but I just wanted to simplify a little bit with a number example just to emphasize the key points when we have a two-dimensional collision with a fixed surface. Parallel to the surface, the speeds remain the same, so the speed before impact is equal to the speed after the impact. And at right angles to the surface, that's where the impulse is provided, so we use our coefficient of restitution formula from chapter 4. Okay, I'll join you now in our second video where we're going to look at a couple of examples from the book.